Mars is not a sanctuary. It never was. Imagine you're standing on the surface of Mars, not in a dome, not in a suit, just standing. The sky above you is the color of bruised copper. The ground beneath your feet is rust and dust and ancient silence. Now imagine taking off your helmet. You wouldn't last 2 minutes. But that's not the frightening part. The frightening part is this. Even with the helmet, even with the suit, even with all the technology we can possibly pack into a spacecraft, there are places on Mars where you still wouldn't survive. Not because of what you can see, but because of what you can't. Invisible radiation that shreds DNA, soil that poisons everything it touches, terrain that makes Everest look like a gentle hill. And somewhere, buried beneath the red dust, a question we're not sure we want to answer. Is there something already there? Tonight, we drift toward Mars. Not the Mars of science fiction, not the terraformed paradise or the bustling colony. We drift toward the real Mars, the one the rovers have been quietly revealing for decades. The one that is beautiful, yes, but also brutal. The one that has drawn us across the solar system, only to remind us that we are visitors here. We will explore its vast canyons, its towering volcanoes, its frozen poles. We will trace the invisible lines that divide what is reachable from what is not. We will ask why some places on this world are so dangerous that even our most advanced technology struggles to survive, let alone human bodies. And we will confront a quiet, humbling truth, that most of Mars may forever remain a place we can only observe from a distance. But before we drift too far, if this journey stirs something in you, if the wonders and mysteries of the cosmos spark wonder inside you, consider subscribing to Calmcosmicdrift. Because this community is built for minds like yours, to wander, to question, and to find a moment of peace in the vastness of it all. Now, let us begin. We have been dreaming of Mars for longer than most people realize. Before telescopes, before rockets, before we even knew it was a world, an actual place with mountains and valleys and weather, it was already burning in our imagination. The ancient astronomers saw it moving across the night sky, a red wanderer, unlike the steady stars around it. They named it after their gods of war, Mars, Ares, the blood-colored one. They saw its reddish glow and imagined it was a world of fire and conflict, a celestial embodiment of everything fierce and untamable. But they never knew what it really was. They never knew it had ice caps that shimmered like Earth's own poles. They never knew it had canyons so vast they could swallow the Grand Canyon whole. They never knew it had seasons and dust storms and evidence of ancient rivers that once carved their way across its surface. That knowledge would take centuries. And when it finally came, when the first spacecraft reached Mars and sent back images that shattered every expectation, something shifted inside us. We didn't just see a planet. We saw a possibility, a place where humanity could begin again. And that dream, that beautiful, stubborn, irrational dream, has never quite let go of us. To understand why Mars has held such a grip on us, we have to go back. Way back. Back to the late 19th century, when a wealthy American astronomer named Percival Lowell built an observatory in the Arizona desert. He had a theory, one that many considered brilliant and others considered madness. Lowell believed he could see canals on Mars, straight, deliberate lines crisscrossing the Martian surface. He sketched them meticulously. He published books about them. He argued that these canals were evidence of an advanced civilization, an ancient, dying race that had built an elaborate network to transport water from the polar ice caps to the parched equatorial regions. He was wrong, of course. The canals were an optical illusion, the result of his own eyes playing tricks on him, aided by the limitations of his telescopes. What he saw as straight lines were actually natural features, geological formations that his mind had connected into something that made sense to him. But the damage, if you can call it that, was already done. Lowell's vision of Mars captured the public imagination. It gave us a Mars that was not just a distant rock, but a place with history, with purpose, with inhabitants who looked up at their own sky and wondered the same things we wondered. It planted a seed, and that seed grew. By the time the 20th century arrived, Mars had become a fixture in our cultural consciousness. Wells wrote about Martian invaders, not the gentle canal builders of Lowell's imagination, but something terrifying, something that looked down on Earth with hungry eyes. His novel, The War of the Worlds, terrified millions when it was broadcast as a radio drama in 1938. People genuinely believed that Martians were landing in New Jersey. The panic was real, a testament to how deeply the idea of Mars had settled into our collective psyche. And then, just a few decades later, the dream shifted again. Mars became a frontier, the next great voyage, the destination that would define a generation. In the 1960s, we were reaching for the moon. But even as Neil Armstrong took those first steps, scientists were already looking past it. Mars was the real prize. The moon was a stepping stone, a proving ground, but Mars was the destination. Wernher von Braun, the man who built the rockets that took us to the moon, drew up plans for a Mars mission in the 1950s. 10 ships, 100 crew members, a voyage that would have taken years and cost billions. It never happened. The political will wasn't there, and the technology wasn't quite ready. But the vision was planted. In the decades that followed, we kept reaching. Mariner 4 flew past Mars in 1965 and sent back the first close-up images of another world. They were grainy, black and white. They showed a cratered, barren surface that looked more like the moon than the Earth-like paradise some had hoped for. But it was Mars, real, actual, within reach. Viking 1 and Viking 2 landed on the surface in 1976. They sent back color images of a red desert under a pink sky. They scooped up soil and tested it for signs of life. The results were inconclusive, tantalizing, but frustrating. Something in the soil reacted to the tests, but no one could say for certain whether it was biology or chemistry. The dream flickered, but it never died. And then came the rovers. Spirit and Opportunity landed in 2004. They were supposed to last 90 days. Opportunity lasted 14 years. A marathon of exploration that transformed everything we thought we knew about Mars. Curiosity followed in 2012. It landed in Gale Crater, a massive depression that was once filled with water. It found evidence of ancient rivers and lakes. It found organic molecules, the building blocks of life. It found a planet that was once, perhaps, as welcoming as Earth. And then Perseverance arrived in 2021. A robot geologist, equipped with instruments that can detect the faintest traces of ancient life. It landed in Jezero Crater, an ancient river delta, and began collecting samples that we hope to bring back to Earth in the coming decade. Each rover has sent back images that take our breath away. Sunset over Mars. A pale blue glow at the horizon. Dust devils dancing across the desert floor. The haunting silhouette of a distant mountain against a faded sky. These images are not science fiction. They are real, and they feed the dream. But there is something else the rovers have shown us, something that has forced us to reconsider everything we once imagined about Mars. They have shown us a world that is beautiful, yes, but also brutal. A world that was never waiting for us. A world that never promised us safety. The same technology that allows us to explore Mars has also revealed its dangers. The radiation that penetrates the thin atmosphere. The toxic soil that clings to everything it touches. The dust storms that can cover the entire planet for weeks at a time. We have mapped Mars more completely than any planet other than Earth. We know its mountains and valleys. We know its weather patterns and its geological history. We know where the water was and where it might still be. And we know, with growing certainty, that most of it is not a place we can safely go. The dream of Mars is not dead, but it has changed. It has matured from a fantasy into a calculation, from a wish into a roadmap, from a simple desire to set foot somewhere new, into a complex question of survival, ethics, and humility. We are still reaching for Mars, but we are reaching with our eyes wide open. There is a map of Mars that most people never see. You've seen the other maps, the ones that hang on classroom walls, the ones that appear in documentaries, the ones that color the red planet in shades of orange and brown, labeling its famous features with names that have become almost familiar. Olympus Mons, Valles Marineris, the polar ice caps, the sprawling plains of Utopia and Elysium. These maps invite us to explore, to imagine walking across those landscapes, to dream of what it would be like to stand on those distant shores. But there is another map, a map that has no colorful topography, no carefully rendered craters, no sweeping canyons or towering mountains. Instead, this map is covered in zones of red, exclusion zones, zones where the words "do not enter" are written in the language of physics, biology, and cold, hard reality. This is the map of Mars that planetary scientists have been quietly assembling for years. And it tells a very different story than the one we grew up with. To understand this map, we need to start with the most fundamental characteristic of Mars, the one that shapes almost everything else: the lack of a global magnetic field. On Earth, we take our magnetic field for granted. We cannot see it. We cannot feel it. But it is there, wrapping our planet like an invisible shield, deflecting the solar wind, a constant stream of charged particles radiating outward from the sun. Without it, our atmosphere would have been stripped away long ago. Without it, the surface of Earth would be bombarded by radiation that would make life impossible. Earth has its magnetic field because of what lies beneath its surface, a churning molten iron core that generates a dynamo effect, a planetary-scale electromagnetic engine that has been running for billions of years. That engine is what protects us. It is the reason we can walk outside without being cooked by cosmic radiation. It is the reason life was able to emerge, to evolve, to thrive. Mars once had a magnetic field too. Billions of years ago, when the planet was younger and its core was still molten, it generated a shield much like Earth's. That shield protected Mars from the solar wind. It allowed the planet to retain a thicker atmosphere. It allowed liquid water to flow across its surface, rivers, lakes, perhaps even oceans. But then, something changed. Mars's core cooled. The dynamo sputtered. The magnetic field weakened, and eventually, it shut down almost completely. The solar wind, which had been held at bay for hundreds of millions of years, suddenly had a direct path to the planet's surface. It stripped away the atmosphere, mile after mile. It evaporated the water. It turned Mars from a world that might have been Earth's twin into the barren, frozen desert we see today. And it left behind a planet that is almost completely unprotected. Today, the surface of Mars receives a constant, relentless bombardment of radiation. Two types, in particular, pose a threat to any living thing that dares to venture there. The first is galactic cosmic rays. These are particles, mostly protons and helium nuclei, that have traveled across the galaxy, accelerated to nearly the speed of light by supernovas and other violent cosmic events. They are incredibly energetic. They penetrate deep into matter. They can pass through the skin of a spacecraft, through the walls of a habitat, through the human body itself, leaving a trail of damaged cells in their wake. On Earth, we are largely shielded from galactic cosmic rays by our atmosphere and our magnetic field. On Mars, there is no such protection. The atmosphere is too thin to stop them. The magnetic field is gone. The surface of Mars is bathed in a rain of high-energy particles that would, over time, cause significant damage to any human explorer. And then there is the second type of radiation, solar energetic particles. These are bursts of radiation emitted by the Sun during solar flares and coronal mass ejections. They don't pose a constant threat like galactic cosmic rays, but when they occur, they can be lethal. A massive solar storm could deliver a dose of radiation that would overwhelm even the best shielding, causing acute radiation sickness in a matter of hours. This is not speculation. This is measured data. We know exactly how much radiation reaches the surface of Mars because we have put instruments there to measure it. The Curiosity rover carries a radiation sensor called RED. It has been continuously monitoring radiation levels on the Martian surface since 2012, and the numbers are sobering. The radiation dose on the surface of Mars is roughly 30 times higher than the dose we receive on Earth from natural sources. Over a 6-month journey through space to get there, an astronaut would receive a dose of radiation similar to the cumulative dose that NASA allows over an entire career. And once they arrive, the exposure continues. Every day, every hour, every moment they spend on the surface. Now, let's translate that into something more personal. Imagine you are standing on Mars. You are inside a habitat, protected from the worst of it. Even so, after just a few months on the surface, the cells in your body would have been damaged by radiation in ways that increase your risk of cancer for the rest of your life. Your DNA would show signs of mutation. Your immune system would be weakened. Your eyes would be at risk of cataracts. Your bone marrow would be stressed. And that's in the best-case scenario, inside a habitat, with shielding, with medical monitoring. Now imagine you venture beyond the habitat. Imagine you walk across the surface of Mars. You are protected by your spacesuit, but spacesuits offer only limited shielding. They are designed to be flexible, not armored. The radiation levels outside the habitat would be higher, significantly higher, than inside. You would be swimming in a sea of invisible particles, each one capable of causing microscopic damage to your body. A single cosmic ray can pass through your cells and break both strands of your DNA. One burst from the Sun could deliver enough radiation to make you sick within hours. This is not a problem that can be solved with better technology alone. It is a problem that is written into the fundamental nature of Mars itself. The planet is small. Its core is cold. Its shield is gone. No amount of engineering can bring it back. So where does this leave us on our map of forbidden zones? The areas of Mars with the highest radiation levels are the ones where the atmosphere is thinnest. The lowlands. The great northern plains that stretch across the equator. The regions that once held oceans but now hold nothing but dust. These are the places where cosmic rays reach the surface most easily. They are also, ironically, the places that are easiest to land on, smooth, flat, accessible. But the radiation map tells a different story. On the map we don't see, those smooth plains are colored red. Exclusion zones. Places where human beings cannot safely linger for long. Places where a habitat would need to be buried under meters of regolith, just to provide adequate shielding. Places where the cost of living is measured not in money, but in cellular damage and cancer risk. And the highlands? The places with thicker, more protective atmosphere? They are harder to reach, steeper, more rugged, more dangerous to land on. They offer better radiation protection, but they also present engineering challenges that push the limits of our technology. Every potential landing site on Mars involves a trade-off between risk and reward. Some are more protected from radiation. Some are more geologically interesting. Some are more practical for landing and habitation. Finding a site that checks all the boxes, that is safe, scientifically valuable, and logistically feasible, is like searching for a needle in a haystack. And so the map of Mars we use for exploration is not the map of simple geography. It is a map of compromise. It is a map that shows us not only where we can go, but also where we cannot, and why. But the radiation is only one layer of the problem, because even if we find a way to shield ourselves from cosmic rays, even if we build habitats buried deep under the surface, even if we protect ourselves from the sun's angry bursts, the ground beneath our feet presents dangers of its own. Dangers that are just as invisible, just as persistent, and, in some ways, even more difficult to address. Because Mars is not just a world without a magnetic field. It is a world with soil that is actively hostile to life. We have been standing on the surface of Mars for a little while now. Inside our habitat, protected from the radiation that falls like invisible rain. But the radiation is not the only thing we must contend with. There is something else, something beneath our feet, that is just as dangerous. The soil, Martian soil, dirt, regolith. Whatever you choose to call it, it covers the entire planet. Thousands of miles of dust and rock, shaped by wind and water and time. To the uninitiated eye, it looks almost familiar. Red, rocky, dusty. It could be a desert on Earth. But it is not, and the differences are not subtle. The first thing you would notice, if you could study Martian soil up close, is its texture. It is fine. Exceptionally fine. The dust particles on Mars are smaller than most dust particles on Earth, about the size of talcum powder. They are also sharp, microscopically sharp, because there is no water on the surface to round them out, no flowing rivers to smooth their edges, no gentle erosion, just the relentless grinding of wind over eons, creating particles that are jagged and abrasive. That dust gets everywhere. We know this from the rovers. Over the years, dust has accumulated on their solar panels, reducing their power output. It has clogged their mechanical joints. It has coated their instruments. Engineers have learned to work around it, but only with difficulty. For human explorers, this dust would be a constant problem. It would get into spacesuits, into habitats, into lungs. And unlike the dust on Earth, this dust is not inert. It is not harmless. It is chemically active and dangerous. Because Martian soil contains perchlorates. To understand perchlorates, we have to look at the chemistry of Mars. Perchlorates are salts. They are composed of chlorine and oxygen, bound together in a structure that is surprisingly common on Mars. The Phoenix lander discovered them in the polar regions in 2008. The Curiosity rover confirmed their presence in Gale Crater. Subsequent missions have found them all over the planet. They are everywhere. On Earth, perchlorates are rare. They occur naturally in some arid environments, but they are most often produced industrially. They are used in rocket fuel, in fireworks, in explosives. They are also used in agriculture, as a defoliant, a chemical that kills unwanted plants, and they are used in the production of certain materials, like rubber. In other words, perchlorates are useful. They are also, to put it plainly, toxic. For humans, exposure to perchlorates interferes with the thyroid gland. The thyroid is responsible for regulating metabolism. It produces hormones that control how the body uses energy. When perchlorates enter the body, they compete with iodine, a critical nutrient that the thyroid needs to function. Over time, this can lead to hypothyroidism, a condition characterized by fatigue, weight gain, depression, and long-term health complications. But that is not the only danger. Perchlorates are also irritants. They can damage the skin. They can damage the lungs. They can damage the digestive system. In high enough concentrations, they can cause respiratory failure. The dust on Mars is everywhere, on the surface, in the atmosphere, coating the rocks and the regolith. Any human explorer would be exposed to it constantly, and when that dust is heated, it becomes even more dangerous. In the presence of heat, perchlorates release oxygen. This is why they are used in rocket fuel. They are a powerful oxidizer, a chemical that fuels combustion. If a spacesuit's heating system reaches a certain temperature, the dust on that suit could ignite. Not explosively, necessarily, but dangerously enough to cause a fire. A fire that would be almost impossible to extinguish in a vacuum. The implications for human exploration are profound. Every step on Mars would kick up dust. Every breath would bring it into the habitat. Every piece of equipment would be coated in it. Cleaning it off would be a constant chore and a constant risk. The dust would become part of the environment, part of the daily struggle to survive, and the solutions are not simple. You cannot just wash the dust away. There is no water to spare. You cannot just filter it out of the air. The particles are too small, too abundant, too persistent. You can build habitats with airlocks, with cleaning stations, with sophisticated filtration systems, but even the best systems would have to contend with an environment that is actively trying to contaminate everything. This is what it means to live on Mars. Not just surviving the radiation, not just surviving the cold, but surviving the very ground beneath your feet. And yet, the story is not entirely bleak. Scientists are working on solutions. There are promising avenues of research. One involves using bacteria to break down perchlorates, biological remediation that could, in theory, clean the soil. Another involves simply burying the soil or covering it with a layer of impermeable material. The most promising approach may be to extract the perchlorates and use them as a resource, a source of oxygen for rocket fuel or for breathing. But these solutions are not ready, and they may not be ready for decades. For now, the perchlorates remain, a hidden danger, written into the chemistry of Mars. Another reason why the map is covered in zones of exclusion. Another reason why so much of the planet is forbidden to human feet. But even if we could solve the problem of radiation, even if we could solve the problem of perchlorate dust, even if we could safely land on Mars and establish a sustainable habitat, There are still places on the planet that we will almost certainly never reach. Places that are forbidden not by chemistry, not by physics, but by something else entirely, by their sheer, overwhelming scale. We have talked about the invisible dangers, radiation that shreds DNA, soil that poisons the body. These are threats that cannot be seen, cannot be felt, cannot be avoided by simply choosing a different path. But there is another kind of danger on Mars, one that is visible, one that is written into the very shape of the planet, one that has been carved over billions of years by forces we are only beginning to understand. The terrain. Mars is a world of extremes. Its mountains are the tallest in the solar system. Its canyons are deeper than anything on Earth. Its valleys stretch for thousands of miles. Its craters are scars from ancient impacts, wounds that have never healed. These are not features you can simply walk around. They are not obstacles you can easily bypass. They are barriers, natural, absolute, and unforgiving. And they cover most of the planet. Let us begin with the most obvious example. Olympus Mons. It is the largest volcano in the solar system. A shield volcano, similar in shape to the volcanoes of Hawaii, but on a scale that defies imagination. It rises 25 kilometers above the surrounding plains. That is nearly 3 times the height of Mount Everest. Its base is 600 kilometers across, roughly the size of the state of Arizona. The caldera at its summit is 80 kilometers wide, large enough to swallow an entire city. To stand at the base of Olympus Mons and look up would be an experience unlike anything on Earth. The volcano is so massive that its slopes curve gently, almost imperceptibly, across the horizon. You would not see the peak from the base. It would be hidden by the curvature of the planet itself. The ascent would take days, not because the climb is steep, but because the distance is so great. And yet, Olympus Mons is not the most dangerous place on Mars. Its slopes are relatively gentle. Its surface is relatively stable. If you had the right equipment, you could, in theory, climb it. But the climb would be exhausting. The altitude would be punishing. The thin atmosphere would offer almost no oxygen, no protection from the cold, no shield against the radiation that bathes the summit. The summit of Olympus Mons is, in many ways, the most exposed place on Mars. The atmosphere is thinner there than anywhere else on the planet. The radiation levels are higher. The temperatures are colder. To stand at the peak would be to stand at the edge of the planet itself, a place where the world below you fades into the void of space. It is not a place for humans, and so it remains on the map of forbidden zones, a destination we can see from orbit, a feature we can study from a distance, a place we will almost certainly never set foot on. Then there is Valles Marineris. If Olympus Mons is the tallest mountain in the solar system, Valles Marineris is the largest canyon. It stretches for more than 4,000 kilometers, roughly the distance from New York to Los Angeles. It is 7 kilometers deep in places and 200 kilometers wide. It is, by any measure, a scar on the face of Mars, a wound that was carved by forces we still do not fully understand. The origins of Valles Marineris are mysterious. It may have been created by tectonic activity, the Martian crust cracking and pulling apart. It may have been carved by water, ancient rivers that once flowed across the surface. It may have been shaped by both, acting over billions of years to create a chasm so vast that it can be seen from Earth with a moderately powerful telescope. But whatever its origins, the canyon is a barrier. Imagine trying to cross it. You stand at the edge, looking down into a depth that exceeds anything on Earth. The walls are steep. The terrain is unstable. The winds that blow through the canyon are fierce, channeled by the narrow walls, accelerated by the temperature differences between the rim and the floor. It would be a journey of days, if not weeks, just to descend to the bottom. And once you arrived, you would find yourself in a world that is almost alien. The atmospheric pressure at the bottom of Valles Marineris is higher than at the rim. The temperatures are warmer. The winds are different. It is like descending into another planet entirely. And yet, for all its dangers, Valles Marineris is also one of the most scientifically valuable places on Mars. The canyon walls expose layers of rock that have been buried for billions of years, a geological timeline that could reveal the planet's entire history. If we could safely reach the bottom, we could study rocks that have been untouched since the time when Mars was wet, warm, and potentially alive. But we cannot reach the bottom, not with current technology, not with current capabilities. The canyon is too deep, too dangerous, too remote. For now, it remains a forbidden zone, a place we can only study from orbit, a tantalizing mystery that is just out of reach. And then there are the poles. The north and south poles of Mars are covered in layers of ice, water ice mixed with frozen carbon dioxide. These ice caps are vast. They contain enough water to cover the entire planet in a layer of liquid nearly a kilometer deep. They are, by any measure, a treasure trove of resources, but they are also incredibly hostile. The temperatures at the poles are the coldest on Mars. At the South Pole, during winter, temperatures can drop to -140 degrees Celsius. That is cold enough to freeze carbon dioxide out of the atmosphere, turning the air into snow. It is cold enough to freeze the blood in your veins. It is cold enough to make even the most advanced spacesuit struggle. And then there is the darkness. During the Martian winter, the poles experience months of continuous night. No sunlight, no warmth, no way to recharge solar panels, no way to maintain habitats without massive power reserves. Any mission to the poles would have to survive the longest, darkest, coldest winter in the solar system. It is not impossible, in theory, but it is close. The poles remain on the map of forbidden zones, places we may eventually reach, but only with technology that does not yet exist, only with resources that we cannot yet afford, only with a commitment that we have not yet made. But there is another kind of terrain that is even more dangerous, one that is not as obvious, one that is not as famous, one that is, in many ways, the most subtle and insidious of all: the dust. Not the perchlorate dust we talked about earlier. That is a chemical hazard. This is different. This is physical, mechanical. The dust of Mars is everywhere, covering the surface, filling the atmosphere, coating every rock and every crater. But it is not just a nuisance. It is a killer. Martian dust storms are the largest in the solar system. They can cover the entire planet. They can last for weeks or months. They can reach speeds of 100 kilometers per hour. Not fast by Earth standards, but dangerous nonetheless, because the dust is so fine. It gets into everything. It clogs filters. It abrades surfaces. It blocks sunlight. It reduces visibility to near zero. It can, and has, threatened robotic missions. The Opportunity rover was lost to a dust storm in 2018, a storm that covered the entire planet and blocked out the sun for months. Its solar panels could no longer generate enough power. Its batteries drained. Its systems shut down. And Opportunity, which had survived for 14 years on a mission designed to last 90 days, fell silent forever. For a human mission, a dust storm would be catastrophic. It would cut off the sun, making solar power impossible. It would reduce visibility, making navigation dangerous. It would clog air filters, making breathing difficult. It would fill habitats with fine abrasive particles that would cause mechanical failures and health problems. And there would be nothing you could do but wait. Weeks, months, stuck inside a habitat, waiting for the storm to pass, waiting for the sky to clear, waiting for the sun to return, watching your supplies dwindle, watching your power reserves drop, watching the dust pile up against your windows, layer by layer, until the world outside is nothing but a muffled red darkness. This is the reality of Mars. The planet does not want you there. It does not care about your dreams. It does not care about your mission. It is a world that has been shaped by forces that are indifferent to life, and it will never be anything else. But even if we could conquer the mountains, even if we could cross the canyons, even if we could survive the dust storms, even if we could endure the cold and the radiation and the toxic soil, there is another boundary we would encounter. Not a physical boundary, a human one. Because the map of forbidden zones is not only drawn by nature, it is also drawn by us. And some of those lines are written in ethics. We have spent this journey exploring the physical barriers that keep us from most of Mars. The radiation, the toxic soil, the impossible terrain. These are forces written into the very fabric of the planet. Laws of nature that no amount of human will can overcome. But there is another kind of barrier. One that is not physical. One that is not chemical. One that is not geological. It is a barrier we create ourselves. A line we draw on the map, not because we cannot cross it, but because we choose not to. These are the preservation zones, and they may be the most important boundaries on Mars. To understand why we would voluntarily limit our own exploration, we have to go back to the beginning. Back to the earliest days of space exploration, when we first began sending probes to other worlds. In the 1960s, as NASA was preparing to send the first missions to the Moon, a group of scientists began to raise concerns. They worried about contamination, not contamination of the astronauts, but contamination of the places they were visiting. They argued that if we were going to search for life on other worlds, we had to be careful not to bring life with us. Earth life, bacterial life, microscopic life that could hitch a ride on a spacecraft and contaminate an otherwise pristine environment. Their concerns were taken seriously. In 1967, the United Nations established the Outer Space Treaty, a document that, among other things, explicitly addressed the issue of planetary protection. The treaty stated that all space exploration should be conducted in a way that avoids harmful contamination of celestial bodies. It was a commitment, a principle, a recognition that the solar system is not ours to spoil. And from that principle, a set of guidelines emerged. The planetary protection categories. They rank destinations based on their potential to harbor life, and based on the risk that we might inadvertently contaminate them. Mars falls into the highest category of protection, because Mars is the most promising place in the solar system to search for life beyond Earth. We have already talked about the evidence, the ancient rivers, the organic molecules, the seasonal methane plumes that appear and disappear with puzzling regularity, the underground lakes of liquid water that may still exist beneath the polar ice caps. These discoveries have transformed our understanding of Mars from a dead world to a world that may, in some sense, still be alive. But we do not know for certain. And that uncertainty is the driving force behind the preservation zones. If there is life on Mars, even microbial life, even life that exists in the most extreme environments, it would be the most significant discovery in the history of science. It would mean we are not alone. It would mean life is not a one-time accident. It would mean the universe is teeming with possibilities. It would change everything. But if we contaminate Mars with Earth life, if we bring our own bacteria, our own microbes, our own biological material, we could destroy that discovery before we have even made it. We would never know if the life we found was native to Mars or imported from Earth. We would have contaminated the very evidence we were trying to find. This is not a hypothetical concern. It is a real one. Every spacecraft that goes to Mars is carefully sterilized before launch. They are baked in ovens. They are wiped with sterilizing agents. They are assembled in clean rooms that are kept as close to sterile as humanly possible. And yet, despite these precautions, we know that it is impossible to sterilize a spacecraft completely. There are always a few hardy microbes that survive. There are always a few spores that cling to the surfaces, hidden in crevices, protected from the heat and the chemicals. We are, in a sense, bringing life to Mars whether we intend to or not. The preservation zones are an attempt to manage this risk. They are areas on Mars that are considered so scientifically valuable, so likely to contain evidence of past or present life, that we have agreed to protect them. No landing, no rovers, no humans. These zones are off-limits, at least for now. At least until we know more. The most important preservation zone on Mars is the region surrounding the ancient river deltas. These are the places where water once flowed from the highlands into the lowlands, carrying sediment and nutrients, and perhaps the building blocks of life. The deltas are rich in clay minerals, the kind of minerals that preserve organic molecules. They are, in many ways, a geological archive, a record of Mars's habitable past, a place where, if life ever existed on the planet, there is a good chance that its remains are still preserved. We have already explored one of these deltas, Jezero Crater. The Perseverance rover is currently exploring it, studying its rocks, and collecting samples for future return to Earth. But even Perseverance is being careful. It is following strict protocols to avoid contamination. It is collecting samples in tubes that will be sealed and stored, preserving them for future analysis. But there are other deltas, other sites, other places where the water once flowed. Some of them are even more promising than Jezero. Some of them may contain evidence of life that is more recent, more accessible, more likely to have survived. These are the places we are protecting. These are the places we are keeping safe, waiting for the day when we can study them properly. And that day may be a long time coming. Because the preservation zones are not just about protecting Mars. They are also about protecting ourselves. If there is life on Mars, it is not necessarily friendly. It may be harmless. It may be beneficial. But it may also be dangerous. A virus, a pathogen, an organism that evolves in an environment completely different from Earth, and that our immune systems have never encountered. Bringing that life back to Earth could be catastrophic. And so, the preservation zones serve another purpose. They create a buffer, a quarantine, a way to ensure that we do not accidentally bring something back that we cannot handle. This is the paradox of the preservation zones. They are barriers that we impose on ourselves. They are boundaries that we respect. They are lines on the map that say, Here be mysteries, and we are not ready to solve them. And yet, these zones are also a source of hope. They are a testament to our growing maturity as a species. We are learning to be careful. We are learning to be patient. We are learning that not everything must be conquered. Not everything must be touched. Not everything must be understood immediately. We are learning to wait. But the preservation zones are not permanent. They are not eternal. They are a temporary measure, a way to protect what is precious until we are ready to protect it ourselves. One day, we will have the technology to explore these zones safely. One day, we will have the knowledge to understand what we find. One day, we will be ready to answer the question that has been burning in our minds for centuries. Is there life on Mars? But until that day, the preservation zones remain. A reminder that sometimes the most powerful thing we can do is not to explore, but to wait. And there is another kind of preservation zone, one that is not about biology, one that is not about contamination, one that is about something more intangible, something that speaks to our deepest values, the preservation of wonder itself. The places that are so beautiful, so extraordinary, so otherworldly, that we have decided to protect them from ourselves, not because they are dangerous, not because they are scientifically valuable, but because they are sacred. We have done this on Earth, the Grand Canyon, the Great Barrier Reef, Antarctica. These are places we have protected, not because we could not reach them, but because we chose not to. We recognize that some things are more valuable when they remain untouched, that the act of leaving them alone is a kind of reverence, a recognition that we are not the owners of this world, but its stewards. The same principle applies to Mars. There are places on the red planet that are so striking, so extraordinary, that we have already begun to think of them as heritage sites. The ice caps, the Valles Marineris, the towering peak of Olympus Mons. These are places we may never visit, not because we cannot, but because we should not. They belong to the planet itself. They are part of Mars's identity. To set foot on them would be to diminish them. It is a strange thought, that the most powerful form of exploration is sometimes to stay away, that the greatest act of discovery is sometimes to leave the mystery intact. But it is a thought that is gaining ground, and it is a thought that will shape our future on Mars. So the preservation zones remain, places we cannot go, places we choose not to go, places we will protect, not out of fear, but out of respect. They are the last lines on our map, the final boundaries, the edges of the forbidden zones. And they are a reminder that the most important exploration is not always outward. Sometimes it is inward, a journey into our own values, a journey into our own capacity for restraint, a journey into what it means to be human in a universe that is vast, mysterious, and sacred, because Mars will always be there. But our chance to preserve its beauty and its secrets is only now. We have traveled far tonight, across a world that has captured our imagination for centuries, across a landscape of impossible mountains, bottomless canyons, and silent plains that stretch farther than the eye can see. We have walked through the invisible dangers, the radiation, the poison, the cold. We have confronted the boundaries we have drawn for ourselves, the preservation zones, the ethical lines, the places we choose not to go. And we have arrived at a quiet, humbling truth. Mars is not a sanctuary. It never was. It never will be. It is a world that was not designed for us. A world that offers no comfort, no safety, no guarantee of survival. It is a place of extremes, a place of danger, a place where the very ground beneath our feet is actively hostile to life. And yet, we still dream of it. We still reach for it. We still look up at that red point of light in the night sky and feel something stir within us. Because Mars is not just a destination, it is a reflection, a mirror held up to our own desires, our own ambitions, our own limitations. It asks us who we are and what we value. It asks us what we are willing to sacrifice, what we are willing to risk, and what we are willing to leave behind. And it asks us, perhaps most importantly, whether we can find meaning in the reaching, even if we never arrive. Because the forbidden zones are not a failure. They are a gift, a reminder that the universe is larger than our ambitions, a reminder that some things are precious precisely because they are out of reach, a reminder that the most profound discoveries are not always the ones we make with our hands, but the ones we make with our minds. The mountains we cannot climb, the canyons we cannot cross, the valleys we cannot explore. They are not obstacles. They are invitations. Invitations to wonder. Invitations to imagine. Invitations to ask the questions that have no answers, and to find peace in the asking. This is what it means to drift, to let go of the need to conquer, to let go of the need to possess, to let go of the need to understand everything, control everything, reach everything, to simply appreciate the beauty of the unreachable, to find wonder in the places we can never go, and to carry that wonder back to the world we inhabit. Mars will always be there, red and distant and achingly beautiful. It will always be a place of mystery, a place of possibility, a place of dreams. But the greatest dream is not the dream of standing on its surface. The greatest dream is the dream of becoming the kind of species that can look at a forbidden zone and feel not frustration, but gratitude. The kind of species that can accept its limits without losing its curiosity. The kind of species that can find meaning not in what it possesses, but in what it is. That is the dream that Mars offers us. Not a new world to claim, but a new perspective on ourselves. Thank you for drifting with us tonight. Until next time.